Welcome to this final session of the AI webinar series. I'll talk about profiling your application using the NVTX extension. I'm Giuseppe Fiameni, the site manager at the NVIDIA AI Technology Center in Italy. And through this presentation, I'm going to introduce you to NVTX extension that you can use while profiling your deep learning applications. What usually happens is that you get a new system with the new GPUs. You install all the software stack, and you start writing your Python program with PyTorch, for instance, and then you suddenly discover that the system is not used at 100%. So the GPU utilization is not that high. And although you did all the best practice, you realize that you are not using the GPUs that you have and all the performance that the system provides. There are different things that you can do to speed up the training of your network. You can use the latest GPU, of course, because if you get the latest GPUs, you get a performance boost without changing your code. But sometimes you have to apply some changes to tune some knobs that your deep learning frameworks provide. You can, of course, update the release of your libraries, and then you can optimize the networking of your system or the storage, but you need to understand how these things work. The problem is that there are a lot of things that are involved from the top of your Python program to the bottom, because there are different layers that may really impact the final performance. You have your deep learning framework, then you need the CPU, the GPU, the system memory, the networking, the drivers, and all the PCI cards. And you have to understand that all these layers, all these components can be tuned and should be tuned to really improve the performance of your code, because the default configurations are not, most of the time, are not suitable for your system. However, deep learning frameworks have a lot of knobs that you might tune. They control the way these frameworks operate, but most of the times they are not set to maximize the performance. The values that you usually get are generic enough to work on all the systems, but they don't reflect the system characteristics. The goal of this presentation is to tell you how to find out which are the knobs that you have to regulate, to tune, to really improve the performance and get rid of bottlenecks. To do that, NVIDIA provides a family of products to profile your application. So the family is called NSIGHT, and there are different components available, different applications that you may use. You have NSIGHT Systems, NSIGHT Compute, NSIGHT Graphics. So the NSIGHT Systems, that is the system that we are going to use, that I'm going to show you in this session, is a system-wide application profiler. Okay, you can use it to profile your application from the CPU to the GPU. You have NSIGHT Compute if you want to optimize, debug your CUDA kernel, NSIGHT Graphics if you want to debug, optimize some specific graphic routines. We also provide plugins for Eclipse or for Visual Studio, and all these frameworks cooperate and share information through this library, which is called CUPT. It's CUDA Profiling Tools Interface. So the NSIGHT Systems, as I was saying you before, is a system-wide profiler. You can check the process trees, the GPU workload, the GPU utilization, the CPU utilization, all the threads and the streams that are used, all the memory transfers from the host to device and the way back, and all the interactions with the system's calls. So it's a very powerful tool that provide you a lot of information. And we also provided a Docker container that you can get from our hub, the NGC. You can launch it, and then you can use it to profile your application. The NSIGHT provides also a command line interface and a graphic interface to plot and see the results of your profiling session. So if you launch a basic profiler, this is what you get. So you get a lot of information. So you see all the streams or the timelines for the different application from the CPUs, all the processes, the threads within each process, whether they are Python or C or Fortran, for instance, all the CUDA libraries that are involved into the execution. So there is a lot of information that you can get. The CPU utilization, the runtime of all the operating system calls, the annotation that you may put into your code, and I will tell you how to do that. All the library of the CUDA-X family, cuBLAS, for instance, in this case, the kernel and the memory transfers, and the utilization of the streams, and all the very low-level calls that the application needs to execute. In order to enrich the information, to extend the information that you get from the profiler, NVIDIA developed this extension toolkit, which is called NVTX. It's an interface, it's a C-based interface that you can use to annotate your application, because the problem is that the profiler doesn't know anything about the application logic. Okay, it doesn't know whether you are doing a training loop or are doing a data transfer. So, but if you really want to get information, you have to start annotating, because otherwise the details that you get are too rich to really understand where the issues, the performance issues are. So this library is integrated within TensorFlow and PyTorch, and you can use this to identify, I don't know, code ranges or specific kernels in your application that might cause the problem. So let's imagine that you have an application that is organized across different layers. This can be a training loop, for instance. You can use NVTX to identify regions, and there is this model start and end. You can identify the region and tell to the profiler, please highlight this region while doing the profiling, and plot where this region starts and where it ends. This is the basic command line that you can use to profile your application. So NSYS profile allows you to trace a lot of information and to collect a lot of the data. The first line tells the system which kind of API you want to trace: the CUDA kernel, the operating system calls, the NVTX tags, the cuDNN layer, or the cuBLAS, for instance. The delayed profile with Y option tells the profiler to start, in this case, after 60 seconds the application started. This is to avoid to collect information about, for instance, the warm-up of the libraries, the loading of the libraries that you need to know is not relevant for your profiling session. For how long you want to profile the application, you can use the option -D for the baseline, the output that you want to get, and if you want to have a summary, a short summary after the end of the profiling. If you launch the profiler in your application and you get the result and you plot it through the NSIGHT visualizer, this is the level of details that you can get. Here we are using the NVTX, okay, but we are not tagging the code. So you can get a higher level of information, because you can see the shape of the tensors, for instance, whether you are doing a math multiplication, but you don't know how these very low-level commands reflect to the application logic. If we take a simple training program, for instance, what you can do with the NVTX is start identifying regions. regions in your code. And for instance, this code starts with a training loop. It's a very basic training loop, and you can use NVTX through a push and pop model to identify the hierarchy across the zones in your code that you want to mark. You can see there are these simple calls towards a CUDA NVTX branch push and branch pop. I have a more details slide about this. You can start from the beginning and tell to the profiler, please identify this is the iteration body. So this is where the iteration starts. It's body iteration number I in this case. This is with the push, you identify the beginning of the region, and with the pop, you identify the end of the region that you are tracking. And in this case, for instance, we have the forward pass and the backward pass. So you can create these blocks with a specific hierarchy. So you will have the iteration, then the forward pass and the backward pass. So this is a very simple training loop. If you put those tags in your application, if you launch the profiler again, this is what you get. So you have the iteration, then the forward pass and the backward pass. So you start understanding what the application is doing. So where the application is when at that specific time. So you have the iteration, that is the macro section, then you have the forward and the backward pass. You can also even go farther. For instance, you can, if you want to understand how much time is spent, for instance, using the mixed precision or not using the mixed precision, you can do things like this. You can use, I don't know, the NVTX tags to identify where the amp region starts, or if you don't want to use amp, if there is a health cycle, you can tell, okay, this is the amp region, this is the region without using amp. So if you want to understand, since you cannot use these two pieces of code at the same time, but you want to understand how much time is spent while using AMP or without using AMP, this is what you can do. So you can create nested regions to identify blocks that you're interested in. Let's try to do a very simple training session. So we take a very a training loop. It's a simple DNN training loop. We use PyTorch. This is the code that you will find in NVIDIA AI Technology Center Toolkit. You use PyTorch and we use CUDA in this case. So the training loop is composed of these simple steps. You copy the data from the device, from the storage, maybe using the DALI library. You do the forward pass, the backward pass, and then at the end you update the weights. Okay, this is a very simple training loop. This is a very simple set of commands that you can use to profile your application. We start blocking the asynchronous threads. So this export is very important because dealing with the asynchronous threads can be very difficult, especially when you profile the application, because you don't know whether the threads have been queued or are waiting for something to happen. It's good practice to block the asynchronous threads and make all them be synchronous while profiling your application. You can test your application with Python run train just to check that everything is okay, and then launch your profiling session. So you prepend the Python run train py command with all the options of the ANSYS. If you launch that command, this is what you get. So basically, you can understand what the application is doing, and in this case, the CPU is waiting for something to happen before feeding the GPU. And if you tag your application using NVTX marks, it becomes super simple to understand where the CPU is waiting. We see that the data loading is taking a very large fraction of the time. Basically, data is used using a single thread, and this makes the GPU wait for too long. One simple tuning is to improve the number of threads or the workers that are used to get the data from the hard drive up to the main memory. The default configuration of most deep learning frameworks is set to 0. This means that only one thread is used to do everything, from moving the data to controlling all the other executions and dealing with all the aggregation. If you increase this number to 8, this will result in a performance boost. What's the best number to put there is something that to figure out by yourself, in the sense that, for instance, if you have a system with 4 GPUs and 40 cores, 10 will be a good number to put there, because the system has 10 cores to control every GPU. But this is something that you have to experiment. It's good practice to always put a larger number than 0, but at a certain point it might enter into a sort of overhead. So the time that you spend in dealing with all the workers might create some inefficiency. After having increased the number of threads, you suddenly realize that the data loading time dropped of several seconds. So in this case, we realized that we have more threads that can take the data from the storage to the main memory and up to the GPU. The tip that I've shown you in the previous slide regards a simple training loop. Here I'm presenting you ResNet 50 that spans across different steps while training the network. We have the batch preprocessing, the forward, the backward pass, and the gradient reduction and weights update. I'm showing this to give you some indications of where the tags, the NVTX tags, could be placed. And one advice is to put the tags at the beginning, at the end of each of these individual steps. In this case, if you do so, you might realize where performance opportunities are. For instance, you might try to improve the way the data is loaded, doing a prefetching of the data for the next iteration, or maybe you can offload the gradient reduction to the nickel library. So this is something that you can only spot while profiling your application. On this slide, you can see the set of software layers that are needed to execute your deep learning workflow. I try to put in evidence where you can tag the code through the NVTX library. For instance, you can tag the PyTorch library, the DALI, or what, but you cannot enrich the information that you get from your profiler over the nickel library, for instance. In this case, if you need to get further information, you have to enable that environment variable, the nickel debug, and put it to info. If you want to execute the training of your network across multiple GPUs or multiple nodes, you have to pay attention to the minimum number of threads that PyTorch needs to use to maximize the load of your system. In this case, I'm presenting you that PyTorch will use at least 8 threads to run efficiently. One as an engine, one to handle the copy of the data, as many as the number of workers that you set, that for DALI should be minimum 3, and 2 threads for forward, one that is going to be used to do the aggregation of floating point 32 weights, another one for the floating point 16 based weights. Let me now share with you some best practices that I hope you will find useful for improving the performance of your training. First of all, it is important that you improve your data loading pipeline to take the data from the hard drive up to the GPU memory. The DALI library can really help with this respect because you can create a pipeline so to keep the GPU busy. DALI is capable to accelerate the data from the storage to the GPU, and also implement some data augmentation techniques that can be directly executed on the GPU. Of course, if you are in a multi-GPU environments, NVLink can really provide high bandwidth and performance across all the GPUs. Enable, wherever it is possible, the mixed precision so that you can leverage the tensor cores that are available in the volta tuning and ampere architectures. This reduces the memory footprint because you are using less space, and also accelerate the training of your network. Through the AMP library, this is automatic, so you can leave the library to decide whether to use the mixed precision, so the scaled precision, the half precision, or the full precision, or a mix between half and full. Make the code work on multiple GPUs. You can parallelize your code using the Horovod library. This will of course speed up the training, and it's very important that you use appropriate interconnection like the NVLink. Another important technique to improve data transfer is through using pinned memory buffers. Host data locations are usually pageable. This means that the GPU cannot access directly the data from a pageable host memory. So when a data transfer occurs, the data needs to be transferred from a pageable memory space to a pinned memory before reaching the device. Okay. For this reason, it's very important that you set the memory to be pinned. In this way, there are no multiple copies to get the data from the host to the device that need to occur. CPU tensors can expose a pinned memory method that can return a copy of the object to that specific pinned region for data that is in that specific pinned region. If you use a pinned tensor space, you can also do asynchronous data transfers. Just passing the no blocking equal to true option to the method to and CUDA of your tensor, you can do data transfer without overlapping the computation. And of course, the data loader needs to know whether you are using pinned memory regions or not. And this is done just using the pin memory option to the data loader constructor. So this is the case of the data loader. You can use a simple data loader and do a pin memory equal to true, or if you have a data structure, you can tell which part of that structure should be in a pinned memory region. Let me share with you a very simple situation where on the left you do have a data loader without using pinned memory regions, while on the right you do. As you can see, without using pinned memory regions, there are a lot of spaces in your timelines, there are a lot of breaks. That means that data is copied twice, first in your pageable space and then in your pinned memory region. If you unlock this using the pinned memory and the non-blocking, so the asynchronous data copy, you see that the timeline does not contain any space. So you are not basically waiting for the data to be copied twice from the pageable space to the GPU memory. This is a very simple technique that you can employ. That can really save a lot of time during the data transfer. Thanks for listening, and please reach out if you have any question.